Welcome everybody in AP Chemistry series. Today we'll end up with section 8.3, which is all about weak acid and base equilibria. So let's start practicing some questions and just pause the video and read the question carefully and try it on your own before we solve it together. The question says that the dissociation of methanoic acid is represented by the equation. A student is given a task of determining the value of Ka for methanoic acid using two different experimental procedures. Calculate the volume in milliliters of 1.5 molar of methanoic acid that the students need to prepare this amount of this one here. We have a concentrated acid, and after adding volume of water, it becomes diluted a little bit. So, which means that we're going to use the vom thing. We're going to dilute the solution. If you don't understand this process well, I'm just going to explain it to you. So, for example, you have the methanoic acid here, all right? This is a concentrated in here. It has 1.5 molar. I'm going to add volume of water, H2O, until the methanoic acid concentrations becomes, M2, until it becomes 0.15 molar. So generally, we're diluting the solution of methanoic acid. How can I solve this question? So first of all, you have to apply the von thing. V1 M1 equals V2 M2. The initial volume is unknown. I don't know how much should I take, so it remains unknown for me. And this is the concentrated form of the methanoic acid. The final volume has to be 50 milliliters, so it's 250 milliliters, all right? And we multiply by the final molarity of the acid, which is 0.15 molar, all right? Here we just divide by 1.5 molar, divided by 1.5 molar. For sure, we're canceling the units. And then the V1 is equal to 25 milliliter. B says, using pH probe, the student determines that the pH of 0.135 molar of methanoic acid is 3.22. Using the pH value, calculate the value of Ka. So first of all, guys, you have to keep in mind, since the equation is given to me in here, okay, I can say, all right, the Ka expression is equal to the concentration of hydronium ion multiplied by the concentration of the conjugate base of the acid over the equilibrium molarity of the weak acid. So how can we do that? First of all, in order to calculate the concentration of H3O plus and HCO2, since they are equal, we need to calculate the concentration of hydronium ion from the value of the pH. All right, the pH is given to us. So if you just remember, if you want to calculate the concentration of hydronium ion from the pH value, you have to say it's 10 to the power negative pH, or the antilog of the pH. And then you have to say it's equal to 10 to the power minus 3.22. And the answer, if you do it in your calculator, you'll end up with 6.02 times 10 to the power negative 4 molar. And just keep in mind, this concentration is the same as the concentration of hydronium ion and the conjugate base of the weak acid. Next, we have to apply the Rice table. So we can see that we have the acid from the equation above in here. Don't forget, I'm just rewrite it again. HCO2, H plus water. We have the reversible errors, and it's H3O plus, in addition to the conjugate base. The initial molarity of the acid is 0.135 molar. It's given to us. You can see it's in here. All right. We don't care about water, and these are zeros at initial concentrations. All right. And then we have to say 0.135 minus x plus x plus x. Since we know the value of x, which represents the concentration of hydronium ion, x is equal to 6.02 times 10 to the power negative 4. And the concentration of the acid, you can say it's subtracted from x. I have to subtract again here. We do this process if you know the value of x, by the way. So we have to say the concentration of the acid, CO2, H, is equal to 0.135 minus the value of 6.02 times 10 to the power negative 4. It's not that significant difference, but anyways, you have to apply this. So the answer is going to be 0.1343. Okay, now we have the concentration of H3O plus, the conjugate base, in addition to the acid. So the Ka is equal to the concentration of H3O plus, and these are equal. You can see the conjugate base are equal. So it's 6.02 multiplied by the same value, all right, over the value of the acid over the concentration of the acid at equilibrium, 1343, and then the answer is equal to 2.70 times 10 to the power negative 6. All right, so we calculated the value of Ka. You can see here. I just want to remind you of what we did. First of all, we took the antilog to calculate the concentration of He3 plus. The concentration of He3O plus is the same as the conjugate base. We applied the Rice table. Since the value of X is known, then I have to subtract it for the molarity of the weak acid. We got the new molarity of the weak acid, and then we substitute it, and we got the value of 2.7 times 10 to the power negative 6. So BII says, calculate the percent dissociation of methanoic acid of this one here. Guys, just keep in mind, the dissociation is the same as the ionization. So don't panic, just like they have the same concept, they have the same meaning. Okay, so since we're dealing with acid, the ionization percentage is equal to the concentration of hydronium ion over the initial concentration of methanoic acid, which is HCO2H, multiplied by 100. So the concentration of H3O plus from the previous example, we can see it's 6.02 multiplied by 10 to the power negative 4 over the initial concentration of methanoic acid, which is 0.135 molar, if you can see. So you can divide over this number, all right, and then multiply it by 100. And if you do that in your calculator, you will end up with 0.45%. So you can see that this small value tells you that this acid is barely dissociating in water.